Hello everyone, we'll go ahead and start with the keto enol tautomers. So you can see here two structures, and this is the ketone. In fact, this is our acetone. So acetone can also exist as this enol tautomer. They are not resonance structures, but we call them as tautomers. Keto tautomer is more than 99.9% and less than 1% we can also find enol tautomer. Tautomers define the location of a double bond and a hydrogen. So the double bond here is between carbon and oxygen. In the enol form, it's between the two carbons. And one of the hydrogens that you have in this alpha carbon now on oxygen in the enol form. For most ketones, keto tautomer is more stable than the enol tautomer. Now this keto enol tautomerism can happen in the acidic medium as well as basic medium. Let's see how the base catalyzed keto enol interconversion takes place. So this is the base hydroxide, and we learned that the alpha carbon carrying alpha hydrogens. So these alpha hydrogens are more acidic. Okay, and due to the resonance stabilization through the carbonyl group, so this is more acidic. So as a result, so the base will take up the hydrogen, acidic hydrogen, and then the carbon hydrogen bond will break and the two electrons will be given to the alpha carbon. And the next step is the two electrons going to form between the carbon and then the carbon oxygen bond opens up, making a single bond right there. Now we lost a hydrogen here to hydroxide and formed a water molecule. Okay, and then what's going to happen is now this is in the form of O negative, having three lone pairs. Oxide ion going to grab a proton from a water molecule. See, this moves to the hydroxide to form a water molecule. It could be this water molecule itself or maybe another water molecule in the medium that the oxide grab the hydrogen. And then you form hydroxide ion, so the base regenerates. So it's a catalytic action, right? So now it's the enol. So the hydrogen that you had in the alpha carbon now on the hydrogen. This is how the base promoted keto enol interconversion takes place. Now let's see how the acid catalyzed keto enol interconversion takes place. Now if it is happening in an acidic medium, you cannot have a strong base like hydroxide. Okay, in acidic medium we never have a strong base, and also in a basic medium we do not have strong acids like a hydronium ion. Now the first thing that happen in acidic medium is carbonyl oxygen basic. So this acts as a base, weak base though. It's going to grab this hydrogen from a hydronium ion and it become protonated. Once it become protonated, then this hydrogen over here will become more feasible to attack by a water molecule. You see, earlier in the basic medium it was a hydroxide because it's a strong base. But now we don't have a strong base. So first we need oxygen to be protonated. Once oxygen is protonated, then the water molecule is basic enough for the alpha hydrogen to remove because this is acidic. Why this happens is now it can gain back the enol tautomer. Okay, so you can how the arrow pushing taking place, the mechanism. The lone pair of the water molecule grab the hydrogen, form the hydronium ion, catalytic action. You start with one hydronium ion, you end up with one hydronium ion acting as a catalyst. So the carbon-hydrogen bond breaks, give its electron to form a bond between the carbon-carbon. Now the carbon-oxygen bond opens up and then we regenerate the enol tautomer. OH group. Okay, so this is how the acid catalyzed keto enol interconversion takes place. Acid catalyzed halogenation. Now if you have a carbonyl group in the presence of a halogen like chlorine, iodine, we can add that either chlorine or iodine or any halogen onto the alpha carbon atom. So this is the alpha carbon. You see the chlorine is added to the alpha carbon. iodine is added to the alpha carbon. So this is again in the presence of the acid. And then we're going to be making one chlorine goes here, the other one forms hydrochloric acid, one iodine attack to this carbon, and then the other one attached to that carbon, and then the other one form hydrogen iodide. And in this process, only one alpha hydrogen is replaced by a halogen. Okay. Let's look at the mechanism. Mechanism for the acid catalyzed halogenation. Now, it should come to your mind now, if it is acid catalyzed, the first thing that's going to happen is always the carbonyl oxygen gets protonated. Okay, once it gets protonated, oxygen will become positively charged because it has now 3 bonds. Now this carbon, alpha carbon, is acidic enough for a water molecule to come and grab the hydrogen and form the enol. We had seen up to this part when we looked at the acid catalyzed keto enol tautomerism, right? So now here, once the enol form is been formed, now you see what's going to happen now. It's going to regenerate the keto form. How? So the not the double bond, the lone pairs on the oxygen forms a double bond with the carbon oxygen, forming a pi bond. And then this pi bond over here going to act as a nucleophile electron rich species, gonna go and attack a bromine. And then it leaves the other bromine. So form a double bond here, and then using these 2 electrons form a bond between the carbon and bromine. So you created this alpha bromo compound. And then the oxygen still having 1 hydrogen on it with a positive charge, another water molecule comes and grabs the hydrogen and forms the keto form. So you start with keto form. The reason that we learned the keto enol tautomerism, you can see in these mechanisms, when a group is attached to the alpha carbon, it goes through formation of the enol. Now you know it forms the enol, and then the enol again helps to brominate or halogenate the alpha carbon through the mechanism. Okay. This is the same as the mechanism for acid catalyzed enolization, except that Br plus is the electrophile instead of H plus. Okay. And then the same thing happened in the presence of a base. Base promoted halogenation. Now you know what's going to happen in the base. When you add a base, do you think this oxygen will get protonated? No. It doesn't, right? So we look at the mechanism. In the presence of excess bromine, in fact, when you do the base promoted halogenation, you can add more than 1 halogen into the alpha carbon, whereas acid catalyzed halogenation, only 1 halogen was added. Okay. Normally, in the presence of a base, all the alpha hydrogens are replaced by halogens. If it was another hydrogen here to begin with, you will see 3 bromine groups attached. Okay. Mechanism, how things work, right? So the base promoted halogenation, you know already this step. Base grab the hydrogen, form the carbon ion, and then form the enolate. We have seen up to this part. And then the same thing like the acid catalyzed halogenation. Now here it's not OH group, it's an oxide O minus. Forming the double bond gives this pi electrons to form a bond between the carbon and bromine. So the bromine is attached to this alpha carbon. Okay. Now the same thing can happen again. Now once you get to this point, it can go from the beginning. Now here you have another alpha hydrogen. This alpha hydrogen will be taken up by this hydroxide. Same process takes place, and then another bromide will be attached. So repeat first 2 steps, and then you can have the same thing again. And if this alkyl group hydrogen, that would also be replaced with another bromine group. This is the same as the mechanism for base promoted enolization, except that the Br plus is the electrophile instead of H plus. Okay. HVZ reaction. What's happening over here? Now, in the previous cases, we had a ketone or an aldehyde. But here you have a carboxylic acid, carbonyl group and the OH. Carboxylic acid can also be protonated, not the protonated, halogenate the alpha carbon. We call that reaction as HVZ, Hell-Volhard-Zelinsky, HVZ reaction. So what are the reagents we need? We need phosphorus tribromide in the presence of bromine. And the second step, when you add water, you can brominate alpha carbon of a carboxylic acid. HVZ reaction replaces the alpha hydrogen of a carboxylic acid with bromine. Okay. Excuse me. So these are the steps in the HVZ reaction. First step, you have a carboxylic acid, you add phosphorus tribromide. So in the OH group of the carboxylic acid will be replaced by bromine. It's going to form acyl bromide. And then the acyl bromide is, once it is been formed, the keto form can go to enol form. Now we know how the keto form comes to enol. We have seen it 2 times now. So once the enol form is been formed, so one of the lone pairs form a double bond, and then the carbon-carbon pi bond breaks and form a bond between the bromine, and it halogenate the alpha carbon. Excuse me. Okay. So you have this protonated oxygen also on the carbonyl group. When you add water, what's going to happen? Water will go and grab this hydrogen, and then now you have an alpha brominated carboxylic acid. So if you want to brominate or halogenate alpha carbon of a carboxylic acid, you can think of doing HVZ reaction. Reacting PBr3 with bromine, and then in the second step adding water. Okay. The carboxylic acid is converted to an acyl bromide. That's the first step, acyl bromide. Acyl bromide's alpha hydrogen is replaced by bromine, alpha hydrogen. Acyl bromide is hydrolyzed back to the carboxylic acid. Okay, so when you add water, not only this removes the hydrogen, it also hydrolyzes the acyl halide. It breaks the bond between carbon and bromine, and then the carboxylic acid can be regenerated. So alpha brominated carboxylic acid when you add water in the second step. Okay. Excuse me. Now we have seen, so most of the alpha halogenation or alpha carbon reactions replacing the hydrogens on the alpha carbon take place through formation of an enolate. So it would be good to know how to form a strong enolate. Okay. We use this reagent called LDA to form an enolate ion. Now if you use enolate using a regular base like hydroxide, let's see what's going to happen. Only a small amount of enolate ion is formed if you just use like a sodium hydroxide, any base. So here we know this hydrogen, alpha hydrogen is acidic. It's going to grab this hydrogen and form the carbon ion, and then the carbon ion form the enolate. Now the enolate is being formed. Now if you look at the pKa of the cyclohexanone, it's 17, and then the pKa of water is 15.7. So between these two, which one is more acidic? This is pKa 17, this is pKa 15.7. So the pKa is the measure of acidity of a weak acid. The lower the pKa, the acid would be more stronger. They are all weak acids, that's why they have a pKa, but pK values will help us to find out among the weak acids which one is a strong weak acid. Okay, so between pKa 17 and pKa 15.7, which one do you think is a strong acid? pKa 15.7. right? So you know that the strong acid and strong base will make weak acid and the weak base. Even though we are going to form the enolate ion with hydroxide, that's going to form only less than 0.1%. Okay. Equilibrium lies to the left. You see the left arrow is more compared to the forward arrow. And these are two resonance structures once this is being formed. Now if you use LDA, LDA is lithium diisopropyl amide. Okay. All the ketone is converted to enolate ion. The equilibrium lies to the right. And the reason being, we're going to look at what is the pKa of the acid that generate after we make the enolate. So this is cyclohexanone, pKa is 17. Lithium diisopropyl amide, that's the base we use, form the enolate. Just like that, because this is the base, gonna grab the hydrogen, form the carbon ion, and this is the resonance forms of that. And then what you are generating at the end is DIA, which is diisopropyl amine. Diisopropyl amine pKa is 35. It's a base. Normally we know amines are bases. Now here we are generating 15.7 pKa water. Here it is more basic, right? Between pKa 17 and pKa 35, which one is a strong acid? Cyclohexanone. So the strong acid with the strong base will give you weak acid and the weak base. Okay, so this is the weak acid. So this is a strong acid, this is the weak acid. Okay, so as a result, we can see almost 100% of the enolate is being formed with LDA. So normally if you want to make an enolate, we use LDA. Now this is the structure of LDA and how it synthesizes. So this is the diisopropyl amine. So this is the isopropyl group with 3 carbons, isopropyl amine. Diisopropyl amine, there are 2 on the amine, and then you add butyl lithium, and this reaction is being done in tetrahydrofuran at minus 78 degrees Celsius. There are 2 ways we can reach negative 78 degrees Celsius. One way is you can run the reaction in liquid nitrogen, minus 78, and then the other way is you put dry ice in acetone, and that will give you negative 78. Okay, and then when you do that, you see there is a hydrogen over there, and this is N-butyl lithium is a base. So this goes and grab this hydrogen and form butane once it grabs a hydrogen, and this generate nitrogen hydrogen bond breaks, so it has a negative charge right there. So that is called lithium diisopropyl amide, and that is the base, okay, that we use. Alkylating an enolate ion. Now we have found a good base that can form an enolate. So when you want to form an enolate, we use LDA in the presence of tetrahydrofuran, and then it's going to grab this hydrogen over here and form the carbon ion. And then you can see the resonance form, this form over here. And then if you want to alkylate alpha carbon, you use any alkyl halide if you want to add ethyl group. So the way it is being added, again the lone pair gives its electrons to form the carbon oxygen pi bond. This pi bond breaks, gives its electron to form a bond with the carbon, primary carbon, and then the leaves bromine. So we can add alkyl group onto the alpha carbon by replacing the alpha hydrogen. So this reaction happens as an SN2 reaction. Okay, this can also be shown as, so this is how the mechanism works. Also you can just show this LDA THF grab the hydrogen over here. Okay, you know what's happening, even though I'm going to show you There is a hydrogen over here. So this is going to grab this hydrogen, gives its electrons to the carbon, alpha carbon, form this carbon ion, and then the carbon ion alkylate in this fashion to add alkyl group onto the alpha carbon. This method also can be used to alkylate the alpha carbon of ketones, esters and nitriles. So what we are looking at here is the ketone, but we can do the same thing for esters and nitrile groups also. What are the nitrile? Nitriles are this group. Okay. Okay, now alkylating esters and nitriles with the same process. So here we have an ester, add LDA tetrahydrofuran, and the alkylating agent is methyl iodide. So we know what's going to happen. LDA always going to grab the alpha hydrogen, form a negative charge here, carbon ion, grabs the carbon methyl group and then alkylate the methyl alpha carbon. Same thing, so this is your nitrile. Okay, you add LDA-THF, carbon, nitrogen. So the alpha carbon to the nitrile is this carbon right there. So the hydrogen here will be deprotonated by the LDA, form a carbon ion. So the ethyl group of the alkyl halide will add on to the alpha carbon of the nitrile over here. Okay. Okay, so now there are two ways that we can form the enolate. The two ways are either we can make a kinetic enolate or we can make a thermodynamic enolate. This gives us two different products. This depends on the type of substrate we use as well as the temperature that we conduct the reaction. Okay, by changing the temperature, we can get the enolate that we desire to achieve the product that we want. Okay, now let's see here we have 2-methyl cyclohexanone. You add lithium diisopropylamide and tetrahydrofuran. So, what's going to happen? You can form the enolate on this carbon. So, there are two alpha hydrogens. Do you see that there are two alpha hydrogens? So this is one alpha hydrogen and there are two alpha hydrogens over here. So when we put LDA, you can LDA either grab this hydrogen, okay, or LDA can take this hydrogen. There are two alpha hydrogens, correct? So let's see if it goes to the go by the green pathway. It's going to generate a negative charge over here and then forms the enolate. Now you guys know how the enolate is being formed. This is the enolate. If this hydrogen is lost by LDA and then when you add the alkyl halide, it's going to alkylate the alpha carbon over here. We call that as the kinetic enolate. Always you can see the kinetic enolate prefers to take the hydrogen from the least hindered alpha hydrogen. So this is more hindered, meaning there is a methyl group. It's difficult to reach there, but here it is more open. It is quick. So kinetic is quick. Kinetic energy, right? Electrons are moving, the molecules are moving fast. Okay, so you can form 2,6-dimethyl cyclohexanone. 2,6-dimethyl cyclohexanone is the major product if the reaction is irreversible, and this reaction is also irreversible, and the reaction is done at very low temperature, negative 78 degrees Celsius. Okay, now the thermodynamic enolate is being formed by forming the most stable enolate. Why it is more stable? Now you see here, for the thermodynamic one, it has more time for the reaction to take place. It has more time to think where I want to go. So the LDA goes and take this hydrogen, form a carbon ion, and then form the enolate. So the enolate is going to be something like that. What's the difference between these two enolates? If you look at these, if you consider these as alkenes, which one do you think is more stable? alkene. How do we look at the stability of alkene? By looking at the substituents on alkene, correct? So this one has a one substituent and a hydrogen, and then this has two substituents. Basically, this alkene is three substituted. Three groups are substituted. This is one group, one group, one group, and this is hydrogen. Let's look at this enolate. How many substituents are on this alkene? This is one substituent, another substituent, another substituent, another one. So this is four substituents on the alkene. So which one is more stable? It is this one. The more substituted the alkene is more stable. So the more stable enolate is being formed through the thermodynamic control. We call it as thermodynamic enolate ion. Thermodynamic enolate happens at a higher temperature. Thermo means temperature. It's not necessarily happen at a very low temperature, whereas the kinetic enolate at -78, but we can form this one at much higher temperature compared to this, which is at 0 degrees Celsius. And 2,2-dimethylhexanone. So when we do the alkylation, so the alkyl group will add on to this carbon. 2,2-dimethylcyclohexanone is a major product if the reaction is reversible. Okay, same LDA we are using. So if you are doing a reaction where you want specifically to attach your alkyl group either to this carbon or to this carbon, by changing the temperature of the reaction mixture, you can achieve what you want. Kinetic enolate ion is formed faster. The thermodynamic enolate ion is more stable. So this is the kinetic enolate. And then this is formed faster because the hydrogen is more accessible and more acidic. Whereas the thermodynamic enolate is this one, CH3. This is the thermodynamic enolate. So this thermodynamic enolate is more stable because the double bond is more substituted. I guess we'll stop here and then we'll start the next session in the third part.